Welcome to the Trimester 2 LEQ. Today, our good friend John Brown reacts 65.10 grams of nitrogen gas with 4.04 grams of hydrogen gas in a closed 20-liter container. The reaction proceeds to equilibrium, producing ammonia, and the total pressure of the container at equilibrium is found to be 4.93 atm. So first, we must write the balance equation for this expression. So we know that our reactants are N2, nitrogen gas, and hydrogen gas, H2, that we will produce NH3, ammonia. So now what we must figure out is what will be the coefficients. So we know that we start with 2 moles of nitrogen on the reactant side, but only 1 mole of nitrogen on the products. And on the reactants, we also have 2 moles of hydrogen versus 3 moles of hydrogen on the reactants. So the first thing we will do is we will add a 2 in front of the NH3. We now have 2 nitrogens on the reactants. That's balanced. And 6 hydrogens on the reactants. So now we have 6 hydrogens on the reactants to 2 hydrogens on... Sorry, we have 6 hydrogens on the products to 2 hydrogens on the reactants. So we must add a 3 in front of the H2. And so we will have the balanced equation. Don't have to add a coefficient to the nitrogen gas. So the next step, it's a bit obscured here by the tape. Find the final temperature of the container in Kelvin. So this is a perf nerd question. Use the equation PV equals nRT. We're given the pressure, the volume, and of course we know the ideal gas constant R, but we aren't exactly given the number of moles. So we must convert from grams to moles. 65.10 grams of N2. The molar mass, 24.02. Of course, you would multiply molar mass of nitrogen by 2, as they are, and then, you get 2.71 moles of nitrogen gas and exactly 2 moles of hydrogen gas. So that gives you in total 4.71 moles. That will be your N. So you get T on its own. Temperature is equal to pressure times volume over number of moles times the ideal gas constant. You plug in all your values and you will get 255 Kelvin is the temperature of this reaction. So now we must find how many moles of ammonia are we producing through this reaction. So first, we need to determine what our limiting reagent is. As we can see, that is hydrogen gas, as we have fewer moles of it. And then we will convert from hydrogen to ammonia via our stoichiometric coefficient. So it takes 3 moles of hydrogen gas to produce 2 moles of ammonia. So we multiply by 2 over 3, and we produce 1.33 moles of ammonia. Next, again, I'm sorry, this is covered up by the tape. Let's try and move this down. It's ridiculous. Whoop. Yes, I'm a perfect. Find the partial pressures at equilibrium of nitrogen and nitrogen gas and hydrogen gas. So we have the number of moles. Now let us find the partial pressures. So the thing with this is that we know that not all of the nitrogen gas is going to react because hydrogen is the limiting reagent. So in order to determine how many moles of each we will have at equilibrium once the ammonia is formed, we will subtract the number of moles of our gas, be that nitrogen or hydrogen gas. We'll subtract the number of moles of ammonium formed divided by our stoichiometric coefficient. So 2.71 minus the 1.33 moles of NH3 created However, we will multiply that by the stoichiometric coefficient, as there's only 1 mole of nitrogen gas for every 2 moles of ammonia. So we get 2.71 times 1.33 divided by 2 is 0.665. And we end up with 2.045 moles of N2 at equilibrium. And for hydrogen, it's much simpler because hydrogen is the limiting reactant, and we're going to consume all of the hydrogen gas. So we will have 0 moles of H2 at equilibrium. So if you were to plug that into the Pervnert equation, then you get 0 ATM. There is no hydrogen at equilibrium, so obviously it's not going to be exerting any pressure on the system. So, but of course we do have to find the pressure of nitrogen gas. P equals nRT over V. Plug in 2.045 moles for the equation, and you will get 4.28 ATM at equilibrium of this total system. 4.28 ATM is from nitrogen gas. So here, for the next part, we have a graph of this reaction. This is supposed to say NH3. This is for ammonia. So, this is a graph you can see on its pressure on the x-axis, obviously because we start with just the reactants. The pressure of the nitrogen hydrogen gas is very high at the start, and then we have no pressure coming from the ammonia. As the reaction progresses, it's going to change, even though nitrogen gas is the most at equilibrium. And we see that there is no hydrogen gas. But if we're looking for at what time the reaction is reaching equilibrium, we just need to look for where do these graphs level out, at what point is there no more movement. And the most clear-cut example, I mean, if you could probably get away with anything between like 15 and 20 minutes, I think the safest thing to do here would be to put it at 20 minutes. That is where the reaction reaches equilibrium according to this graph. So next, we have more tape blocking the question. We must calculate the reaction quotient we must calculate the reaction quotient. So the first thing we need to do is we need to find the partial pressure of ammonia, because we did not calculate that. According to Dalton's law of partial pressures, the total pressure of the system is equal to the sum of all the partial pressures. Since we know that the total pressure is 4.93, and the partial pressures of the other gases are 4.28 and 0, we can just do 4.93 minus 4.28, and we find that the partial pressure of NH3 is 0.65. So then we do the reaction quotient. The partial pressure of the products raised to the coefficient over partial pressure of the reactants raised to the coefficient. Because of the reaction quotient, we're not including the partial pressure of hydrogen gas, which, as we know, is 0. So we plug in 0.65 squared over 2.43. It gives us a reaction quotient of 1.74 times 10 to the negative second. Next, we will use this information to determine, so from this reaction quotient, will the reaction shift towards forming more products, towards forming more reactants, or do we not know? Just based on the information given. So the answer is we cannot conclusively determine, because we don't know the equilibrium coefficient. We know that if QP, this is supposed to say QP. QP. If QP is less than KP, then we know that the reaction will have to shift towards the right. If QP is greater than KP, it'll have to shift towards the left. But KP is undefined because we have 0 partial pressure of hydrogen at equilibrium. So at equilibrium, you would see we would have like 0 times like 2.43 over 0.65 square, and that would give us undefined. We can't have that. So because we don't know the equilibrium constant, we can't definitively say whether whether we will see the reaction shift towards more products or more reactants. We can kind of assume, based on the fact that QP is relatively small because it's less than 1, we can sort of assume that it would probably shift towards more reactants, but we can't definitively say without experimentation or just further analysis. Just based on the information given, we can't exactly say. So next, John Brown is not satisfied with the reaction as is. He wants to shift it to favor the formation of more products. So I asked the student, the unlucky test taker, to identify 2 ways in which he could shift it towards the products. And there are more than 2 answers to this, probably, but these are just 2 that you could use. That would be 2 of the more apparent ones. So first, you could decrease the volume or increase the pressure, because pressure and volume are inversely related. Those would both be doing the same thing. So when you do this, when you decrease the volume, increase the pressure, the equilibrium will shift towards the side that has fewer moles of gas. In this case, on the reactant side of 2 moles of gas, the product side has 2 moles of gas. The reactant side has 4 moles of gas. So we're going to shift towards the products, that side with fewer moles of gas. So increasing the pressure, decreasing the volume would increase products. And then the other thing would be just adding more nitrogen gas or hydrogen gas, more so the nitrogen, because again, hydrogen gas, no partial pressure at equilibrium. But according to Le Chatelier's principle, when we add more of the reactant, we are going to shift away from the reactants. The system is going to shift towards the formation of more products in order to reestablish that equilibrium. So if you added nitrogen gas, it's gonna see, okay, we have too much nitrogen gas now. We need to shift towards the production of ammonia so that everything will be balanced. And so the next one, this tells us the enthalpy value. So the change in enthalpy of this reaction is negative 16 kilojoules per mole. So when you go through this reaction, you will lose, like, each mole of gas will lose 16 kilojoules. So John Brown now increases the temperature of the system by 20 degrees. When he increases the system, how will this shift the equilibrium? Will it shift towards the products, or will it shift it towards the reactants? So the answer is that it will shift towards the reactants. So this is an exothermic system. It's an exothermic reaction because heat temperature is being released when we have the reaction. The temperature of the nitrogen gas and the energy in the nitrogen gas and the hydrogen gas is being released into the system. So, because when we increase the temperature of an exothermic system, the heat will be considered a product. When heat is considered a product, because of like Le Chatelier's principle, now that we have an extra product, it's going to shift towards production on the reactant side. So if we increase the temperature of an exothermic system, it's going to shift towards the reactants in order to preserve that equilibrium balance. Finally, the last question, calculate the change in energy of this reaction. So there's no specific heat value given. That's because we have the enthalpy value of their reaction, the delta H of reaction. We have the number of moles, and that's all we need. We just need to convert we have the number of kilojoules per mole that this reaction will release. We have the number of moles, that is 1.33. And so our final, this will release 21.28 kilojoules of energy. It will produce the nitrogen and the hydrogen will lose 21.28 kilojoules through this reaction. And there we go. Thank you.